Okay, so here we have a robot arm. We are in example number 2 of chapter 12, section 12.8. So the robot arm is extending a constant rate of r. So this is extension of the robot arm is measuring r dot 1.5 feet per second. So that's our velocity. And they are giving us the position at that moment, which is r 3 meters. So this is the length of the arm is 3 feet. 3 feet for that instant. They are giving us also information about the c, so the height of that arm, which is 4 times the time square in feet, and they are given also information about how that rotates in theta. So this is a perfect example to use cylindrical coordinates because we are given information in theta, r, and c. So I already wrote down here the expressions for velocity and acceleration, and those are in your formula sheet. So we did in the theoretical background that you saw in the narrated lectures, you saw where those expressions come from. But I don't expect you to learn them by heart, but I do expect you to learn where they come from. Obviously, it comes from the same as usual, that the velocity is the derivative of the position and the acceleration is the derivative of the velocity. But in this case, we have a coordinate system that is moving with my particle, that in this case is A, right? So since we are, that's a coordinate system that is moving with the robot arm. Therefore, when you derive the expression of the position, then comes the derivative also not only of the magnitude, but also of the unit vectors. So please review the theory. So in this case, since we will use these expressions right here, we have to find every single component. So the solution for this example is trying to find all these components. So for the r, I have that is 3 feet, right? R dot is given, and actually they say that is constant. So since it's constant, the r2 dot is equals to 0. Then I have, for theta, is given, that is 0.5 t radians. Then I have to derive this expression to get theta dot. Theta dot will be equals to 0.5 radians per seconds, radians over second, and theta 2 dot will be equals to 0 because we don't have time anymore, and we are deriving respect to time. And then we have c, which is 4 times time square. So c dot will be equals to, let's write it like that. So which will be equals to 4 times 2 times time, and theta 2 dot will be equals to 8. So here we see that we have, let me put that the units because I use the units in all. So that will be feet times over second, and this will be feet second square. So as you see, we have all the components, because we have all the components to substitute our values in our equations. So to get the velocity, we substitute our, which is a vector. Be careful, I really want to make sure we understand the difference between a vector and a scalar, right? Those are vector expressions because we have 3 components, and those are scalar expressions because already are given for a specific direction, right? So this is my velocity as a vector, and I have r dot, which is 1.5 in the r direction, right? Plus r, which is 3, times theta dot, which is 0.5, u sub theta, plus c dot, which is 8 times the time. And the time is 3 seconds. So I'm going to substitute the time as well. So finally, my expression for the velocity will be equals to 1.5 in the r direction plus 4. Let me see. This is 1.5. Let me see. This is 1.5. Oh, sorry. I have a mistake in the, here is 1. Sorry, because I want to make sure that I have the same results that I have here in my paper. This is actually 1.5, and then obviously this is 1.5 and 1.5. So this is 1.5. So that's why I get here 4.5 in theta direction. And here I get 24 in c direction. If I want to get the magnitude, so this is a vector expression, and the magnitude will be the square root of all these terms to square, right? So the magnitude will be equals to the square root of 1.5 plus 4.5 plus 24. Therefore, the velocity, the magnitude of the velocity is 24.5. So this is the magnitude of the velocity. For the acceleration, we do very similar. So this is a vector, and this is a scalar, because the magnitude is a scalar expression. So here we have the acceleration, and we do very similar. We just substitute our values in this expression right here. So we have r2 dot is 0. So let me just mark as 0 the expressions right here. So this is 0, and this is 0 as well. So that makes it a little bit shorter an expression, right? So that will be equals to negative r times theta dot square. This is the r direction. Then we have 2 times r dot will be 1.5 times theta dot, which is also 1.5, and the other term is 0. So that's in my theta direction, and then I have theta dot, which is 8. I'm going to write it right here. The acceleration is, as a vector, is equals to negative 6.75 in the r direction plus 4.5 in the theta direction and 8 in the c direction. And of course, this is a vector expression as we did with the velocity. And if we want to get the magnitude in the same way that we got the velocity, we have to square root every single component to the square, and I get the magnitude. I will just write the magnitude, which is 1.4 mega square. That's feet square. Feet second square. And remember, of course, that this comes from the magnitude will be the square root of 6.75 square plus 4.5 square plus 8 square. And that's the two variables we were asked to find for 3 seconds. So that's the vector. This is a scalar again. So this is the velocity and the acceleration in magnitude for t equals 3 seconds.